talk about horizons with the structure of the principal Iwan bundle. So in this case, non-trivial principal bundle. So that's how this functionality is meant to be understood. It's a topic I've been working on for a couple of years. It's my pleasure to tell you some recent results, mainly about the horizons sections that are Riemann surfaces with genus higher than 0, so essentially everything except for the sphere, and also about the horizons so that this U1 action does not coincide with the null direction. Okay, so I think there are at least two more talks touching on the isolated horizons, but mine is first, so let me introduce some basic notions. So why do we bother with isolated horizons? Well, mainly to have an object that captures as much of the structure of event horizons or event horizons without going to any global notion. So without global total structure or without global Killing vector space. So the definition is modeled on the Killing horizon. So we take our horizon to be a three-dimensional null surface. We can degenerate metric tensor, and because of this degeneracy, at every point we have a null. Every point of the horizon we have a null direction, which together forms a null vector field, and seems to show that this vector field is actually a symmetry. It's a Killing vector of this dimensional metric. Actually, we assume that's not expanding, so that the horizon does not expand. So we can project down this null direction to a space that we usually call the space of the null generators, or just a section of the horizon. So the most interesting cases are obviously when this S is a two-dimensional compact surface, and this is precisely on this surface we have this two-dimensional Riemannian metric, and so downstairs we can have the usual notion of the unique torsionless metric connection. However, this is not enough to determine the connection in the whole horizon. So we also need to introduce one form omega, which is essentially the derivative of this null direction. So similar to the Killing horizons, we define the surface gravity as the self-acceleration along this Killing vector field, and also very interesting for our purposes will be this pseudo-scalar invariant, which I denote by the capital omega, and every object with the superscript 2 will be meant that it lives on this dimensional surface S. And so far this definition, I think, is called just non-expanding horizon. So to be for isolated horizon, we also need to impose this condition, which is usually called being stationary to the second order, which means that the derivative and the connection commute, and also that the Riemann tensor is right.
Sorry, what do you mean by the Riemann tensor of G?
I mean, definitely, if you consider the embedded horizons, then you know what is the Riemann tensor just restricted to the horizon.
G is the general. So what do? You don't. How do you compute the Riemann tensor of G?
I mean, in the embedded, when the horizon embedded to the spacetime. So that's okay. So maybe yeah.
But isn't that implied by this derivative of this connection being 0? Can that be 0 and this second derivative not be 0?
we were intrinsic on A, on the dimension of the null surface, or we treat this as an embedded free surface in false spacetime. Because, you know, for example, what does it mean now? What do you mean now? On null surface, there is no unique choice of digital compatibility.
Maybe we will allow the speaker to speak and Matthias will explain later.
The role of the speaker is to speak.
That's the main role.
Yeah, okay. And the public to listen.
Okay. So if I could take this later, so for isolated horizons, the only rescaling of kappa and L is just scaling variable constant, so it makes sense to, for example, speak about the horizon being extremal or not. Okay, so so far could see that the horizon has a fiber structure over the base space S, but you can show that it's even more. So you have the action. You can show that the action generated by the flow of this spinning vector field acts freely and transitively. So it's a principal bundles, really principal bundle. And also, as we are interested in the connected orbits, we really have the case of this grouping R or one, so just a circle. When the non-trivial cases are the cases with U1. Okay, so with this you can also interpret this omega defined previously as something to do with bundle connection. So actually, if you can introduce the connection in this manner, assuming that the omega tilde is abstract and acting on this null direction you have one. So if you scale it just like kappa, then it's satisfied. In similar notion, we can also see that this scalar invariant omega is connected to curvature, so I'll probably refer to the shorthandly as a connection curvature on the bundle. Okay, so what is the main tool that we use? It's something that we call the Petrov Type D equation. So of course the horizon, if it's embedded, then it's easy to show that. Then the type D just means that the byte tensor has two double principal null direction. However, you can express this condition in terms of objects which are defined intrinsically on the horizon. So for us, this condition means that this invariant is non-vanishing, where vector k everywhere will be just Gaussian curvature of the section, and then introducing some null coframe. Einstein equations on the horizon can be just written. Imply this type D equation, which is the second degree PDE acting on this, from solution of which you will recover the k and I. Okay, so first I'll talk about the horizon of sections such that the genus is higher than 0. So this case has been partially studied in the, without any reference to the bundle structure, so which in the language of my talk means that just that the bundle was a trivial one. So so it was shown that both k and omega has to be constant, and actually that capital omega has to be further 0. So there will be a slight split between the toroidal case and the case of genus higher than 1, but this is mostly due to the fact that with the torus you can actually write some coordinates and do something explicit, which is not so easy in the higher genus case. So torus being just a product of two circles, then we can issue us two coordinates, which are discontinuous at 0 to pi, but apart from that they are fine, and from the fact that this k is constant, we get just the flat metric, and the omega is essentially just a closed one. And for the higher genus, what is easily shown, or what can be shown, is that the case is expressed by genus and area, except for where the k takes a special value, which makes this invariant bunch. So that's why we exclude it. So in the higher genus case, basically the same calculation goes through, but now you don't have this condition that omega has to be 0. In fact, you just focus on omega being non-zero. So a question arises about how many such horizons or bundles we can construct, and those are some very well-known results in the theory of principal bundles, that the classes of isomorphism of this one bundles over any surface S is just essentially the first Chern class. And it's also a basic result that S is oriented and compact without boundary, all of which is the case, then this group is just, the second cosmology group is just integers, so essentially our bundles are numbered by integers. And maybe there's a slight remark also to be had here. So of course this omega, when this omega defined on S, so downstairs is unique only up to gauge, but also up to close by not exact, so one form, so that so they are not just gauge. One forms which are which is the result of whereas there are cohomological units vanishing, which is the dimension implies the genus. Okay, so again on the torus we can actually make some explicit picture, also set and have some explicit formulae. So the flat metric is again what we look for, and then we cannot introduce this connection one form uniquely on the whole base plate, because this boundary is meant to be non-trivial, so we do it by covering the torus with two sets. So one is the one circle except for the 0, where 0 is excluded because, well, one of the coordinates, let's say pi or psi, is not continuous there, times the other circle, and the other part is the same, but with only think of the psi equal to pi. And then you can impose this curvature condition and look at one forms transforming to the one gauge transformation, and can show that, for example, those one satisfy those conditions. Well, maybe the second one is written somewhat strangely, but it's actually a smooth one form, and this fact that it's defined piecewise, and also that we have this strange pi psi minus pi is just an artifact of the fact that psi is not really a globally defined coordinate. Okay, so in the higher genus case, again, we resort to stating some facts about the Gaussian curvature of the section, which is the same as before, and also about this pseudo-scalar invariant omega, which connects this one bit number n, surface gravity, and the area of the horizon. So another natural question is where such horizons are embeddable. So we had some intuitions about the C1 horizons and assumed that they would be embeddable in the generalization of Taub-NUT de Sitter spacetimes. So if it's the first time that you see such metric, the important features are that there is a parameter epsilon, which is 0 plus minus 1, which basically dictates the sign of the curvature of local two surfaces parameterized by zeta and zeta bar coordinates. And that it's a slight generalization of Fallsheet metric. So if you take the spherical case of epsilon being 1 and make this transformation, you get either Taub-NUT, which is regular Taub-NUT is either, or put it as either Fallsheet with oscillation constant. And of course, we have to interpret those spacetimes a la Misner. One of the implications of the Misner interpretation is that the T is now a cyclic coordinate, and it's exactly parameterizing the orbits of our U1 generating, U1 symmetry generating Key vector field. And yeah, so for our case, the important is epsilon equal to 0, which is the planar case, and then the torus follows by, and the torus is just quotient of the plane by some grid, and the higher genus of them is maybe less obvious fact that all of them can be constructed as a quotients of the hyperboloid, so the epsilon minus 1 by some subgroup of the symmetries of this hyperboloid. So we actually show this explicitly by constructing such embedding spacetime. So this construction follows both the structure of this metric and of the structure that we assume about the horizon. So we take as a compact Riemann surface with Riemann manifold, Riemann metric with this unimodular curvature. Assume that we have a bundle over U1 bundle over this surface, satisfying the same connection spherical curvature condition, and that we have the field which is now with respect to this metric, and so that the connection is suitably normalized for this spark connection. And we answer the space-time, which you don't have to look hard enough to realize that it's just maybe concise or rewriting of this general form of the metric. And actually, knowing the curvature of these two surfaces S and this relation is enough to write down the Einstein equation. Einstein equations, solve them, and show that this F is really just the same as in the generalized Taub-NUT ADS case. So the embedding spacetime is at least locally asymmetric to the generalized Taub-NUT ADS. Of course, you would rather you would also have to perform some Eddington-Finkelstein like cofferent transformation, but this doesn't really change the structure equations. So we finally that to arrive to land on the metric which actually covers the horizon. Horizon, of course, corresponding to the 0 of this function f. So maybe the takeaway message from this is that given any omega or k, we can choose the space and parameters such that the contained horizon has the values that we have found in the abstract calculation from the type D equation. The other two interesting facts are that this bundle structure, of course, in quite natural manner extends the bundle structure defined on the entire space-time. So we just extend this bundle by R. And then the role of the connection is played by this guy. You can show that, I mean, it's quite clear that acting on the vector field L, it just gives 1 as before, and that it's the interact. So maybe some interesting comments is that all of those omegas, as I have said, are defined only up to at least up to the first Ryłko homology group. So locally, you can always realize this as a change of the coordinates. However, as we have seen, for example, in the toric case, those coordinates usually do not extend, are not globally well defined. So this is this local diffeomorphism does not extend to a global one. So we have actually globally different space-time, and this sometimes has been referred to in gravitational analog of Harmon bond text. Something that's locally the same, but global properties are different. I want to also say at least some things about these horizons with transversal bundle action. So maybe this is not the most natural structure that you would consider just thinking about horizons, but we have actually quite a good motivation to be interested in those spacetimes. So previously we've been interested in the horizons, in Yuan horizons over the sphere. And at least one of the class of the solutions, which is more richer in this spherical case, could be, we expected it to be embedded in this Kerr-NUT ADS spacetimes. And if we to do that, we took the action as before to be the same as generating horizon. However, there was an additional problem, namely that still there was on the space of the null generators, there was persisting conical singularity unless some condition on parameters was satisfied. So this wasn't quite satisfactory, so our solution was to just consider try to impose a bundle structure with an action which is generated by an arbitrary linear combination of two Kinnick vector fields of accelerated Kerr-NUT and S, with this D being a constant which is suitably chosen and determined by space-time parameters. And in doing so, we actually constructed a space-time which is smooth, which contained a smooth horizon, but now the space-time of null generators had conical singularities. So what we had thought to do was to introduce these horizons with transversal action. So what is the basic construction? As with the torus, you take a sphere and cover it with two patches. One of them is everything except for the south pole, which is this P of pi, and 0 refer to the value of theta. The second one is the same, but without the northern pole. And propose this kind of magic. So what is the maybe question which one ought to ask before, or what is a conical singularity? So conical singularity is usually understood as an effect or as a way of arriving at an answer that we have chosen the wrong scale of the angular coordinate. So of course you can always scale your coordinates such that at one pole the conical singularity vanishes, and can actually say that this metric satisfies this condition. So if you look at the coefficient pi, then in the pole is this coefficient just like a sine square, so the same as just for a regular sphere, and similarly for the other part, just with the second pole, and you glue them by this transition map, which you can also rephrase that the V is now a periodic coordinate, so this D generates this one function. So and yeah, of course, you also need to check that our one-form rotation one-forms are well satisfied in respective poles, which apparently you can also do if you choose suitable kappa. So the result of this exercise in geometry is that you can always take a sphere with conical singularities and get rid of those conical singularities by by adding just one direction and introducing this under structure. So very, very briefly, we have also solved the Petrov Type D equation in this type, introducing coordinates adapted to the axial symmetry. But now, usually one assumes two conditions, that this P frame function vanishes to the poles, and that the derivative has some suitable value, which we now didn't assume this condition, and found that the most important class of the solution, the most general, can be parameterized by four constants. So the four is also the number of parameters in accelerated Kerr-NUT ADS spacetime, and we found this coalescence to be embeddable in our suitably glued accelerated Kerr-NUT ADSs. Okay, so thanks. That will be all from me.
Thank you very much. Questions? Jacek? You got a question now.
Yeah, maybe I will discuss that
Later. Okay. More questions? Please.
Can you hear me?
Yes, yes.
In 2+1 dimensional gravity, conical defects are topological defects with curvature blowing up. And in your case, do I understand correctly that these conical defects, in your case, can be simply removed by a redefinition of coordinates, or they are more pathological?
Well, you can always do it in at least one of the poles. Of course, if you don't do this, then the metric is not continuous or anything else. But yeah, we take the conical singularity just to mean the wrong choice of the angular coordinate, and that if you scale it, then everything will be fine. So.
Okay.
Alexander, there are no more questions, so thank you very much.